Hello, my name is Peter Cummings. I'm the John R. Hall Professor of Chemical and Biomolecular Engineering at Vanderbilt University. Thank you for your interest in our perspective paper, recently published in the Journal of Physical Chemistry Letters, reviewing research conducted with my colleagues Guangfeng, Song Li, and Volker Presser. In recent years, supercapacitors, also called electrical double-layer capacitors or ultracapacitors, have attracted significant attention as a new class of electrical energy storage devices. Since supercapacitors have much higher energy density than conventional capacitors and significantly higher power density than most batteries. When electrical potential is applied between the two electrodes of a supercapacitor, the anions and cations will migrate into the positively or negatively charged electrodes, and an electrical double layer forms at the electrolyte-electrode interface, as shown here. Since the energy of supercapacitors is physically stored in such double layers, the investigation of the double layer at the electrode-electrolyte interface is the key to supercapacitor development. Room temperature ionic liquids are composed entirely of cations and anions without any solvent, and often feature complex organic groups. As their name implies, they are salts which are found to be liquid at room temperature. Room temperature ionic liquids are emerging as very promising candidates in supercapacitors as electrolytes due to their quite wide electrochemical window, excellent thermal stability, non-volatility, and relatively inert nature. In particular, their extended electrochemical potential helps to improve the energy density of supercapacitors. With respect to the electrodes, carbons have become the most widely used electrode material in supercapacitors because of their high specific area, good electrical conductivity, chemical stability in a variety of electrolytes, and relatively low cost. To date, diverse forms of carbon have been developed for supercapacitor electrodes. For example, activated carbon, carbide-derived carbons, carbon nanotubes, carbon onions, and graphene. In this perspective, we investigated ionic liquid-based supercapacitors with different carbon electrodes.
To enhance the supercapacitor's energy density, porous carbons are developed as promising electrodes due to their high surface area. As described in this cartoon, if a pore was introduced to electrode, the electrode surface area will be increased and more charge can be stored, which results a higher energy density. Our research in this perspective is computational using molecular dynamic simulation. Molecular dynamic simulation is a popular and powerful technique for computing equilibrium and transport properties of a classical many-body system at atomic level. Typically, the electrical double layer in supercapacitor is less than a few nanometers in thickness, suggesting that it is essentially a molecular phenomenon. Therefore, molecular dynamic simulation is well suited for modeling supercapacitors. For example, we modeled the pore in carbon electrode as a slit formed by two planar graphene sheets. We used the ion liquid as an electrolyte. When a potential was applied, more count ions can move inside the slit. Using this simulation setup, we studied how the pore size D influences the capacitance. As shown in this graph of capacitance versus pore size, we can see that as the pore size decreases from 1 nanometer, the capacitance increases and reaches a maximum at 0.7 nanometer, and then decreases. This capacitance behavior agrees very well with experimental results. As the pore size increases from 1 to 1.8 nanometer, a second peak occurs, which is a new feature revealed by molecular dynamic simulation for the first time. This double-peaked capacitance pore size curve not only shows a good agreement with experimental results for the first peak, but also invites more experimental work to explore the new feature of the second peak. It also provides a possible explanation for the absence of capacitance increase at micropoles in some experiments.
Clearly, porous carbons could enhance the energy density of supercapacitor. However, the narrow micropoles on electrodes may slow down the charging-discharging rate because of limited ion mobilities. To increase the power density, recently, supercapacitors with curved electrode has been developed, which has positive curved surfaces and can be readily accessible for electrolyte ions, such as carbon nanotubes and carbon anions. In this case, we performed molecular dynamics simulations of carbon nanotubes and carbon anion-based supercapacitors using ionic liquid as electrolytes. We investigate the influence of electrode size and electrode potential on the capacitance of supercapacitors with these curved electrodes. The differential capacitance as a function of potential was shown here. We can see that there is a bell-shaped capacitance versus potential curve for planar electrode, which agrees with previous studies. For the supercapacitors based on carbon nanotubes and carbon anions, the differential capacitance depends weakly on the electrode potential, and this feature becomes more pronounced with the decrease of electrode size. The capacitance for both carbon nanotubes and carbon anions are higher than that near planar graphene. This weak potential dependence of the capacitance will invite further experimental exploration and could benefit the future design and improvement of supercapacitors with stable performance by fabricating electrode surfaces.
In summary, molecular dynamics simulations constitute a unique tool to provide detailed molecular insights into the capacitive behavior of ionic liquid-based supercapacitors with different types of carbon electrodes. It is also worthwhile to note that the electrode surface used here is idealized as planar, cylindrical, or spherical. In the future, more realistic modeling will be required to fully understand the intricacies in capacitive charge storage of carbon supercapacitors based on ionic liquids. We want to thank JPC Letters for providing us with this opportunity of contributing this perspective. JPC Letters is emerging as a very high-impact, interdisciplinary, and rapid publication journal. We are convinced that it is a highly appropriate venue to publish our research. Thank you for your time watching this video.